Yes, so it's a great pleasure for me to introduce Louise Dolan from the University of North Carolina, and she's going to talk about scattering and field theory, and she'll explain it herself.
Okay, so thanks very much for the invitation, and it's just so great to see everyone that I haven't seen for so long, and especially thanks to Peter for all the fun and great ideas so far that I've experienced with him. So I wanted to talk mainly today, more of a specific talk rather than an overview talk of work that I did with Peter Goddard at Princeton after he became the director in around 2003. And in particular, I'll talk about these first three papers here, give highlights on the so-called CHY formulation, which reproduces Feynman graphs as contour integrals over the zeros of certain scattering functions, scattering equations. We'll also then show the polynomial form of those equations and also talk about expressions like this for individual Feynman graphs rather than partial amplitudes. So there were also other papers I did with Peter at Princeton, but I won't focus on them so much today. But I'm just showing you this list to show you that he was not idle while he was director of the Institute for Advanced Study. He was really busy working away. So Freeman Dyson once said to me, "It's so good that Peter is doing physics. I guess maybe all the other directors they had often weren't doing physics while they were there." So just to be clear, this was not the first time I had worked with Peter Goddard. I think I first met him around 1982 when he invited me to come to Cambridge. And after a couple of years of, I think maybe I had met Mike Green in one of the conferences out in the western part of the United States, and I'd been working on something called Kac-Moody algebras, these loop algebras that Graham was talking about. And Michael said, you really must work on string theory. And I thought, well, it's hard enough for me to get a job just working on regular physics, and working on string theory would be even harder. But I took him to heart, and I began to work on a paper of compactifying the type 2 string from 10 down to 4 dimensions. But it wasn't a unitary construction, and it was only the group SU2 to the 6th, the gauge group that came out from that compactification. And so around 1986, I ran into Peter, I think, out in Aspen, and I was telling him about the work, and so he began what was unfamiliar to me at the time, but became very familiar to me after a while, was he would sort of understand what I knew, and then he would begin to talk to me at that level of what I knew. And so he wrote here, you can see that he has changed the group from SU2 to the 6th to this more realistic looking group at SU3 cross SO5, which of course contains the standard model group. He did that by fermionizing the internal degrees of freedom of the string. And he also understood how we could make it a unitary theory. So it was like he had taken this rather unformed piece of physics and turned it into something that I thought was truly fabulous. And this was a series of 4 papers. You can see back in 1986, there was no real general use of email. And this was the second in the series of 4, where he was visiting Santa Barbara at the time. I was working at Rockefeller University in Manhattan in New York. And you could see that this was just the way that the communication happened. And and was perfectly effective as far as I was concerned. So we also at that time did other papers, worked on representations of conformal field theories using representations for the finite groups, the sporadic groups, the monster group. But there was a lot of really interesting physics that I won't discuss today. And then, 20 years later or so, in 2007, Peter has already been the director at the Institute for Advanced Study in Princeton for 4 years. And we're at this London Mathematical Society meeting up in Durham. And he's just, as Nima Arkhani always says, he's just one of us here, even though he was being director of the Institute. And you can see a lot of people that everybody knows. Mike is there, and Bernard DeWitt, and Penrose, and Philip Candelas, and it was a really great gang of people. And I have, if you're interested in that photo, I have a list here of everybody that's in that photo, numbered on their faces. So I want to talk a little bit about these so-called CHY constructions of field theory amplitudes. So what you heard earlier today is all about Peter's contributions to string theory. And in a sense, this work is very much relying on understanding concepts in string theory. But at this point, you're just working on the gauge field theory amplitudes. And as a warm-up, start with just a scalar theory, not even the gauge theory, this so-called lambda phi cubed theory. And the graphs that I've written here, you could just calculate using the Heisenberg picture, going to the interaction picture, using Wick's theorem, and calculating a series of Feynman graphs and getting a total answer. So these ST and U are the Mandelstam invariants. It's a four-dimensional calculation, if you will. The partial amplitude we define as sort of a piece of the total amplitude, and then by summing permutations of the partial amplitude, you can get back to the total amplitude. So these partial amplitudes, when you do a gauge theory version, they will become a gauge invariant piece of the total amplitude. So they're an interesting subset of graphs. And that's what CHY focused on to reproduce the partial amplitudes. These are tree amplitudes to begin with. And the idea is that you can have a contour integration around a multidimensional contour integral. And the path is encircling the zeros of a set of functions, FA, that are given here. So KA are the momenta, and the ZA and B are, we call them worldsheet variables. They're variables in the complex plane, and they're not a string, not coming from a string calculation here, but just from this sort of magic that CHY was putting forward as proposing as related to field theory amplitudes. Now, these scattering equations were first written down. These equations were first written down almost 40 years before by David Fairley and his student Roberts. And they were after a variation of the Veneziano model that was free of tachyons. And in fact, I don't even think their paper was published, but there certainly was a Durham preprint. And so there they stood. And this many years later, Kajazalho and Wan figured out that if you insert these into this contour integration, they proposed that you would get out the actual field theory amplitudes. And the psi here is a function. If it's 1, you get back to the phi cubed scalar theory. If psi is a more complicated determinant of a matrix, that you get to a gauge theory, etc., to gravity, etc., changing psi. These are Mobius invariant. The integrand is not fully conformally invariant, but it does have SU 1, 1 symmetry. So what Peter and I did around 2014 was we proved that this conjecture of CHY was indeed the field theory amplitudes that they had much evidence for. And it, to this day, remains somewhat of a mystery of how you can get out a formula that would normally come from a local quantum field and a Lagrangian for that quantum field, and then doing a Fourier transform on those correlation functions that, with no reference to any kind of locality here or quantum physics, you just get the answer for tree-level scattering by some magical equations. So I wanted to just give you a little bit of flavor of the proof of that formula, of why that works for all the field theory amplitudes. So this is a slide that is discussing any type of field theory amplitude that has these simple poles. And the idea is that you start with a standard amplitude and you shift two of the coordinates, K2 and Kn, let's say, by a certain amount of, I'm sorry, I've just gone through past one slide. You start with the field theory amplitude, you shift two of the coordinates. L mu is a vector here, and C is just some parameter that, if these are simple poles in like K2 dot K1, etc., then the amplitude as a function of the shifted variable C can be rewritten just as in terms of its residues over the simple pole. So the idea is that if you calculate what that residue is, and you can do that if you think of 1 over S or plus 1 over T, one of the simple kinematic invariants, then if you shift S, K1 plus K2 squared, if you K1 plus K2 plus this CL, then the pole will, you can locate where those poles are in C. And here's this pi m, this sum of these momenta. And the idea is that you can then express the residue at that pole by some formula which relates the residue of an n-dimensional endpoint, or an endpoint function down to endpoint functions where n is less than capital N. So if you have a 4-point function, you can relate it as a product of 3-point functions. And so this general procedure, which works for any representation of an amplitude, not just CHY, is called the BCFW relations of Brito, Kajazal, Feng, and Witten. And so our proof for the CHY formula was just to follow this concept of BCFW, but to show that this amplitude, which is the CHY formula, actually satisfies this relation. So that was the general gist of the proof. And at the end of it, you can see what is happening is that the multi-dimensional contour integration, if you divvy it up into various pieces of the product of the different DZAs, that some of them will go with one of the amplitudes, some of them will go with the other sub-amplitude, and then you do the DCM integration so that the residue of that function comes out in this form. And so since that residue is also written as a product of lower endpoint functions, and in fact the same product of lower endpoint functions that standard BCFW relations had, then we have proved that the CHY formulation will satisfy the BCFW relations. And since we know they're true for n equal 4 or n equal 3, you can get them for higher n. That's the idea of this proof. So first we did it just for the standard scalar theory, and then since people were really interested in the gauge theory calculations, we inserted this function into under the contour integration, which promoted the lambda-phi cube theory up to the gauge theory. And this Bathian representation, the square root of the antisymmetric matrix, determinant of the antisymmetric matrix, it's just a features that it will also factorize and follow the same argument for BCFW. So after this concept of proving it for that the CHY formulations really were the field theory answers, we tried to understand what these scattering equations were. They were fairly, I'm sorry, I just haven't learned this yet. Here I go. It's these equations, this sum set equal to 0, and it just seems rather torturous to have the z variables down in the denominator. So the idea is that we understood that you could see that this had a certain symmetry to that set of scattering equations, this Mobius symmetry. And I have that construction here that this is a Mobius invariant quantity, and if you take, here's the Mobius transformations, and if you take the derivative of this thing, you'll get this FA structure out from it. And so if FA equals 0 is a solution, and you do a Mobius transformation, it's still a solution. So because of those infinitesimal symmetries, you could eliminate 3 of the equations. And instead of having A running from 1 to n, so f sub A was n equations, there's now n minus 3 equations, and then they will have generally n minus 3 factorial solutions. We can talk a little bit more about those solutions in a minute, but the general idea is that we're trying to understand how to get a better interpretation for these equations. So the polynomial form, so here originally the z's are down, what David and his student found was the z's were down in the denominator, and we wanted to put the z's up in the numerator to get polynomials in z's. And so this construction for p mu, this is what David Fairley did when he was writing down how he got the scattering equations out, was he looked at this, instead of p mu being the standard Veneziano form, he looked at k mu just divided by some z's, and then to force that p squared had no poles, you could rewrite this just by partial fractions into this form. And so this piece of it had to vanish for this to have no poles. The double pole vanished by the one shell condition, the k squared was 0, and the single poles vanished by the fact you're setting this f equal to 0. And so from there, if you just multiply this p squared up by some more of these z minus zc's, then you can get out that there is a structure that has to be also 0. So each coefficient of the z at that point. So those polynomials that I've defined down here, so the zu is just z1 z times z2. It's a product of the z's for whatever set u you're on. The ku is just a sum of k1 plus k2 plus k3 quantity squared, whatever set you're on. And so, for example, for n equal 4, you would just have one of these polynomials, and it would look like some quadratic in the z's. And here it is involving all of the invariants, s and t and u. So these were, in some sense, a unique Mobius invariant set of polynomial equations. And we felt that maybe there was something fundamental, just as in an algebraic sense, about those equations. So the amplitudes, written back in terms of the h's now instead of the f's, these are the polynomials, have a somewhat similar form. It would be a little harder to prove use the BCFW relations in this form, but it had the advantage of the fact that the polynomials were a very interesting set. I mean, the scattering equations were already interesting, but the polynomial equations would just seemed much more, you could access them easier. So these equations now, by Bezout's theorem, you could actually understand why there was this n minus 3 factorial set of solutions, because there's a set of polynomials for any given capital N, h1, h2, up to h sub n minus 3, and the order of those polynomials is that subscript, so h1 is order 1, h2 is order 2, etc. And by Bezout's theorem, you just multiply if you have a system of algebraic equations, you multiply the order of each of the equations, and the product of those orders is equal to the number of solutions of the equation. And here they are, scattering equations. And you can see you get more and more of them depending on what the number of points, the endpoint function you're interested in solving. And the z2 and the z3, those are the variables, and they get to higher and higher order. And the k1, k2 is just these invariants that you get when you have more than n equal 4. So it's the generalization of the Mandelstam invariance when n is greater than 4. So this was the set of equations that were the scattering equations, or were equivalent to the scattering equations. And so if you now think about the amplitudes that we're getting from these equations, you have the polynomials sitting down here. Is if you actually do that contour integration, it's really just a sum over the solutions of those zeros, of those equations. And so here's the determinant of the polynomials to get the denominator of the sum, and the rest of it is just follows the formulas we had earlier. So at this point, we're just trying to say that there's a set of equations, and you can think of the ideal of those polynomials, and then the solution to those polynomials equal to 0. That's called the variety. And so what we're doing here is trying to understand the amplitude as an object, some type of object, this object, that's attached to this set of solutions, this variety. Now, this was a while back, and it's not clear that this approach is really taking off as far as understanding then how to do the loop equations, etc. But nonetheless, it is a very tight analysis of what is happening at tree level and has put it into this more geometric language. So what we then understood would be interesting is if you could relax those conditions that you were on shell, that k squared was 0. And so that all seemed pretty fundamental from the fact of looking at the construction of the polynomials to start with, where we used that T of z and showed there was no double poles in it because of the on-shell conditions. So what we did for the off-shell treatment, the idea if this was really going to be extendable to loops, and there has been a lot of work done on CHY being extended to loops, but if you just follow your nose, you need to get in the way that Feynman integral would calculate loops is you've got to get off shell to calculate the loop amplitude. And so we understood that if we looked at a construction of what I'll call the off-shell version of the H, and it has a little tilde on it, that this that you could rewrite it in this form where these Kij's were not just any combination of K1 plus K2 up to Kj, but they were consecutive combinations. So in the example I showed before, we had S and T and U. But U, of course, is K1 plus K3 squared. And so what we first noticed was that, or people had known before, but we brought it into play, that the set of number of independent off-shell invariants can be just written in terms of consecutive quantities. So you could just use S12, and that's S, that's K1 plus K2 squared, S23, K2 plus K3 squared, S123 if you had 4 or 5, if you have a higher point function. And you could, of course, always write U, as K1 plus K3, back in terms of S and T and K1 squared and K2 squared, et cetera. And furthermore, it turned out that these amplitudes didn't involve, the off-shell amplitudes didn't involve just K1 squared or K2 squared. They only involved K1 squared through the quantities S12 or S23, et cetera. So we could count how many independent variables there were and express the old one-shell polynomials in terms of these consecutive invariants, and then we could take everything off shell. So that was the plan, and when you did that, for example, for the 4-point polynomial, you now have it, it's not so nice in terms of just Z1, Z2, et cetera. It's this more complicated product, but there's no U. It's just in terms of the consecutive kinematic invariants. So that took us off shell, and then we also understood that not only could you go off shell and have the polynomials, but you could write the rest of the stuff that was in the CHY integrand, not for a whole sum, like 1 over S plus 1 over T, not for the partial amplitude, but for the individual graph, like the 1 over S itself. And so the idea is you take any old Feynman graph, a tree-level graph, and you look at all the places it will have poles in momenta, and you form this sort of Kobe-Nielsen type analysis, which was coming from the understanding of string theory, and take the sites that are closest to the particular pole you want to consider and make this cross ratio out of those z's, and then that product of all the different u's that you would have if you had different poles in a given single Feynman graph, then you would now write that amplitude, again, is a contour integral, but a slightly different integrand. It doesn't have quite as much stuff in it, and then it has this 1 over this product of cross ratios. So again, as an example of that, I just wrote this out by hand, so hopefully you can read it. If you take the 5-point function, it will be a product of 2 poles. If you calculated that, so let's say from just using regular Feynman graph techniques. And if you want to interpret it as a contour integral, then you can take this pole, 1 over S23, that coming from the sum of those 3 momenta, this pole on the left, and put that diagram that we had on the previous page in this way. And so this closest z's here are the 1, 2, 4, and 5, and then you form this cross ratio. And then if you do the same thing with this pole as the center term in that diagram, then you would get a slightly different cross ratio. And so the CHY, the contour integral representation for that single graph, is this product of these cross ratios in the numerator and then the polynomials. You're going around the zeros of these polynomials and the rest of the stuff that was there. So you can then, you think it's going to be a difficult calculation to go around the zeros of these polynomials because they got to be higher and higher order, and you don't want to be solving those polynomials, but you can, for these multi-dimensional contour integrals, you can use the global residue theorem to switch the contour circling the zeros of this to circling a different set of zeros, and that is what is done here schematically. And so what we felt was having a better understanding of the individual graphs and also having them now off-shell, that maybe ultimately one could begin to see how to glue them together to make loops. And so finally, to really have a sense that we knew this was true for all n, that this idea of the cross ratios would really work, we developed a recurrence relation just for a single graph that was off-shell, relating the graph with endpoints. I'm so sorry, I just haven't learned this. Relating the endpoint graph down to an n-1 point graph. And so you hear for the 5-point function, basically you're lopping off this 1, 3, 4 leg here, and then what's left is the 1, 5, 2, 1, 5, 2 with 3, 4. So, and we proved this recurrence relation again, and so that it works for any n, and so we know it works for, go from n equal 3 to n equal 4, n equal 4, and n equal 5, and then you can just know that that representation in terms of the cross ratios is indeed giving you the graphs you would get by a Feynman calculation. All right, so that's sort of the end of the discussion of CHY, and I just wanted to talk a little bit more about other work that Peter has done. Certainly, from Graham's talk today, he understood the tremendous interactions of the Kac-Moody algebras, the loop algebra, the loop group, and the Virasoro algebra. And this was a really well-worn, at least in my library, a well-worn volume of a set of reprints that Peter and David Olive put together, but had a just tremendous paper that they had really reviewed a lot of the details and set up a lot of the framework of our current understanding of Kac-Moody algebras and Virasoro algebras. I remember Victor Katz once said to me, the great thing about Peter Goddard is that you can actually construct all of these things that he as a mathematician had been thinking about for a while, but never quite knew how to write down and have examples of. And so I think there was a really big appreciation, even in the math community, in the algebra community, for the work that of the Goddard and Olive paper that appears in this reprint volume. So I'm not going to discuss the Kac-Moody algebras, but I thought since we talk a little bit about beyond what I did with Peter, just for the last part, to talk about this conformal Yangian construction. Now, you heard a lot about two-dimensional conformal field theories, and also Werner will talk about them. So in 2 dimensions, the conformal group is somewhat different than it is in all the other dimensions, because it has this infinite set of Virasoro generators. But it turns out that the conformal group, as you get up to 4 dimensions, of course, is becoming a 15-dimensional Lie algebra. That group is also very interesting. And it's interesting for 4-dimensional gauge theories. And so I thought I would just show that a little bit here, and instead of focusing just on 4 dimensions, we can think about field theories and gauge theories in n dimensions. And so what I talked about earlier was the CHY construction, and what I'd like to talk about now is the symmetries of that, or at least the symmetries of the field theory amplitudes. So if n is 4, if you're in 4 dimensions, then the conformal group is SO2, 4, and it has the standard translations and rotations, the scale transformation, and the special conformal transformation. And the way this analysis is going to be set up is that if you have an n-point function, you define a copy of this algebra for at each site. And so that's what the little I index is, just running from 1 to n. And so there's 2 things happening here. There's the conformal group itself, and there's also this infinite dimensional extension of the conformal group. It's not exactly a Kac-Moody algebra that maps from S1 into G, not S1 into the conformal group, but it's a Hopf, it's going to be a Hopf algebra, not a Lie algebra, but a Hopf algebra construction. And it will, the Yangian, first written down by Drinfeld in the context of beta ansatz and scattering theory of quantum systems. The Yangian is it's in the same equivalence class as Kac-Moody algebras, but it will have, instead of the Lie algebra with TA, the commutator of TA with TB is just the structure constants times TC. It'll have plus TTT. It'll have more stuff on the right-hand side that's not linear. It's not a Lie algebra. And it will turn out that that's an interesting structure for 4-dimensional gauge theory. So the so-called coproduct construction, or the way of looking at the representations, or you can get the underlying conformal algebra here. You can either call them by their original names, or you can relabel them all as a set of J's. And then you have this level 1 representation, where it's a representation of a level 1 generator. So the idea is that, so in addition to the level 0 generators, that sort of your friends of the SO2, n group, you can have sort of set of level 1 generators, and their products the construction, if you look here, is that it's a product of two of the level 0 of the original generators. So here are the level 1 generators. So the idea is you've got more stuff commuting with the 15, if you have four dimensions, the 15 generators of the conformal. So here is the what they call the defining relations. It's hard to write down the commutation relations of the Yangian because unlike the Kac-Moody where you just have TNA with TMB is FABC, TC, N plus M. Now, if you take two of these, a level 1 with another level 1, you get a level 2, but then, as I said, you get plus some level 0 stuff. So there's an infinite tower, just like in Kac-Moody, the Tn labeled on the integers, but this doesn't really form a Lie algebra. So to write it down in a compact form, you can look at how the level 0 goes with the level 1, and these are just the conformal structure constants. And here is the defining relation that tells you the sort of commutator of this nested commutator has to be back equal to a symmetric product of level 0 generators. So here you can begin to see, can't totally see it here, but the idea is if you take two J hats with each other, you won't just get one other thing here, but you'll get a sum of terms of generators on the right-hand side. So as I said, it's a Hopf algebra construction, and not any old representation of this algebra or of the level 0 generators, not any old representation of the conformal group will actually satisfy this. So the fact that if you have 0 sites, if you just have one site, then J hat will be 0 because J hat was defined on 2 sites. And so you get a condition that 0 is equal to this thing on one site. So the representations of these level 0 generators has to satisfy that Serre condition. And it will turn out that this generator P hat defined in this way, and if you give for the representations of these differential expressions that we had, so if P mu is just the sum of the K1 mu plus K2 mu, etc., and the L mu's are K1 d by d, K2, etc., then that representation will satisfy the Serre relation. And so this is, for example, a really legitimate level 1 generator that would be part of the family of these Yangian transformations. And so this invariant, where you have consecutive from K1 up to Kj squared, if the level 1 generator acts on it, it acts in a very simple way, it turns out, just as a multiplicative factor times the original invariant. And then since the off-shell amplitudes are given by this formula, and the K, the only place the momentum is appearing is in that polynomial. So you can then understand how the level 1 generators would act on this amplitude by just knowing how the level 1 generator acts on the polynomial. So this is the way that the level 1 generators act. And here is the n equal 4 partial amplitude. If we're back to that. And you can see that the way it acts is, it first of all doesn't give 0, so the Yangian is not a symmetry of this partial amplitude. And secondly, it doesn't even return the amplitude. It gives you this 1 over S2 there, but then these are not related to the original amplitude you started with. But if you look at it, p hat now acting on the individual graph, so like just 1 over S, for example, then it will turn out that when you act with that level 1 generator, you do get, again, just this multiplicative factor times the amplitude. And so if you define what they call the extended version of the Yangian, or you can call it what you like, but you just take these factors and you add them to the original definition of the level 1 generators, and that set will also close a Yangian algebra. Of course, that depends on just which graph you've got. But if you have an individual graph, you can get an annihilation by this sort of extended generator. And so the last slide here is that if you now do this for the gauge theory, which is really what people are most interested in, then if you act with the level 1 generator on a 4-point gluon coupling at tree level, you, again, do not get 0, so there's no symmetry. But what you do get is as though you had some type of, what you get is you get an answer, and you can interpret that as had you been acting on this amplitude with this so-called set of super conformal charges. Now, in the Yangian of conformal field theory, there is no super charges, but if you just understood that if you could define these Qs in a way to move the A into some type of spin 1/2 field, then indeed, if you took this combination of minus p mu minus this set, you would get that that combination would annihilate the amplitude. And this is the statement, of course, that the Yangian of PSU224, the Yangian of the superalgebra, annihilates the n=4 superconformal field theory. That's a result that James Drummond found, and also that Chiara Nappi and Ed Witten and I had worked on, understanding that the Yangian was a symmetry of the Yang-Mills theory. But I guess what I was trying to do in this last couple of slides was to show you that if you just consider the conformal algebra itself without a lot of supersymmetry, what you're led to is the way that that conformal algebra acts is it gives out not a 0, but it's some type of fermionic structure. So even in the pure Yang-Mills theory, maybe if there was some other type of fermionic structure, that the conformal symmetry could lead you to that. That was my general conclusion from this. So here's the last slide. And it's just that I'm wishing Peter many happy returns, and also that there's a lot of blank space here for him to keep working. Thank you.
Much. Are there any questions or comments? So these Yangian symmetries, do they allow you to sort of write down closed formulas for the n=4 amplitudes, because you get probably infinitely many additional constraints beyond just conformal symmetry?
You mean once you know that the Yangian symmetry is a symmetry of it?
Can you use this as a way of calculating the amplitudes efficiently?
I don't think it generates the amplitudes. I think once you have the amplitude, you can show they're invariant.
But does it reduce the number of free cross ratios, or does it reduce the number of independent variables on which the amplitude can depend?
it's not, in some sense, it is a differential equation for the
I see.
differential in the momentum. It's a differential equation for the amplitude. So yes, in that sense. Yes.
Can you use Feynman tree theorem to go to loops?
Did you hear his question? He wants to know if we can use the Feynman tree theorem to go to higher loops. Maybe. I haven't done it yet.
Okay, because it,
Yes, but I do have that book where that article is written by Feynman.
Okay, so let's thank Louise again.